All right, let's talk limits. So if you're coming here from algebra or pre-calculus or even geometry, God forbid, limits are an entirely new concept because limits are describing how a function acts as it approaches a certain number, as it gets close to a certain number. And when I say close, I mean infinitely close. And that's different than that's intrinsically different than what you mean when you try to say how does or what is a function at a certain number, because sometimes it differs, like with this instance here. If you want to evaluate the function at the number 4, it would be this number here because that's the closed dot, so -3. But how it acts at or near 4 differs. So let's talk about that for a minute. First, our first problem here is what's the limit as x approaches 0 plus of f of x, our function here. So limit as x approaches 0 plus. What does that even mean? So first of all, if you're trying to find a limit where x is or x approaches 0, basically what that means is you want to start, I'm going to use a different color. You're starting here away from 0 on the positive side, hence the plus, and you want to approach 0. So you want to get infinitely close to 0, and you want to see how this function acts as you get closer and closer and closer to 0 from a positive side, because we specified 0 positive. So we want to know how this function acts as it approaches 0. Well, we can see here that as it approaches 0, it gets closer and closer to our y-intercept, which our y-intercept in this case is 2. So that means that, judging by this graph, it is indeed the number 2. So now we want to find how it approaches from the negative side. So from the negative side, we would then just start out over here and then walk our way to 0 on the x-axis. So then as our function, we would start right here and then walk our way up here and approach from the left side, hence the negative. So it still approaches the same number, our y-intercept, which is 2. So that means both limits from both sides are 2. Now, our next question is limit f of x as x approaches 0 without a plus or minus. What is that now? So this basically just means if you don't have a plus or minus, it just means as you approach from any side, which means now we're including both sides. So this limit here only exists when you have an answer for both the positive and negative side that equal the same thing. And if they do equal the same thing, then your limit as x approaches 0 without a plus or minus exists, and it's just the same number. If these two are different, then this will not exist. It'll literally just straight up not exist. And we'll see that as we come to a different problem. So now limit f of x as x approaches -1 from the positive side. So -1 is right here, which is this little vertical asymptote. So from the positive side, we're going to do the same thing. We're going to start over here and then move our way this way. So we're going to see this function goes here and then down to infinity. So what's really useful about limits is that we can actually use them to describe how infinity works. So as this function here approaches -1, as it gets closer and closer to -1, the value down here gets bigger and bigger and bigger in the negative direction until you get to -1, which you never actually do if you're trying to talk about literals, but this is calculus. So that means that it will, for the limit, approach -infinity. So that means, I'm going to use a different color. I don't know why I picked up blue. So f of x from the positive side is -infinity. So then limit f of x as x approaches -1 from the negative side, same deal. Start over here, approach negative, and again, it is -infinity. So then limit f, this is supposed to be, why are there 2? I wrote 2 of them. I'm going to just erase this one. So limit f of x as x approaches -1 can only exist if both the limits from approaching both sides are the same number, which means limit of f of x as x approaches -1 from either side is negative infinity. Now, limit f of x as x approaches 4 from the positive side. Now, here's where things will start to get a little different. So we're going to start over here, creep our way this way. So we're going to start over here, creep our way this way. And so that means that as f of x approaches 4, from this side, it gets closer and closer to the number 2 without ever actually touching 2. We don't need it to touch 2. We just need it to approach 2 from the positive side, which means get infinitely close without actually getting to the number 2, which means we're going to get infinitely close to this number 2 here, or I keep saying 2, I mean 4. If I'm talking about the x, infinitely close to the number 4 without actually getting there, which means we're getting infinitely close on the y-axis to the number 2 without actually getting there, which means the limit as x approaches from that side is 2. Now you probably are asking a question like, wait, why isn't it -3? -3 is what it actually equals at 2. We don't care what it actually equals. We only care how it acts as it approaches something. So as it approaches this, it gets closer and closer to 2 and never actually reaches 2. So now we can erase these little arrows. Now we do the same thing here with f of x from the negative side. So we approach from the negative side and go up this way. And then we get closer and closer to 4 without ever actually touching 4. But in this case, it's a closed dot, so we do actually touch 4. And so that means we would go up and up and up and up until we reach -3. Now, notice we didn't hop over. There is no hopping in this case. You don't do that. That's just straight up not something you do with limits. Now, let's say, for instance, I were trying to find it at 5 and it was telling me approach to the negative side. Then I would just either start here and then hop over here because I'm going to 5. I'm not going to 4 anymore. Or I would literally just start up here and then go up that way. So I would completely ignore that from the start. But we're not. We're talking about 4. So that means we have these here. So limit f of x as x approaches 4. It differs depending on what direction you're coming from. So that means our answer, because they're different, D and E, does not exist. And whether or not this does not exist is actually important. You'll see in chapter 2.5. So now that we have this, we're going to try to solve limits based on specific things. So what I'm going to do is I'm going to erase all this. Now I have my other lovely whiteboard here with limit laws. Now, before we actually go through any of the problems, I'm just going to talk about what these laws mean. So, because we want to now solve limits not given a graph, we want to solve limits given a function. So, our first one here, limit as x approaches any number a of f of x plus, minus, or multiplied by g of x. So, function plus, minus, multiplied by another function, the limit of all of that, is equal to the limit of f of x plus, minus, or multiplied by the limit as x approaches g of x. This is also supposed to be an a. So that means basically if I'm trying to find the limit of f of x plus g of x, let's say I'm just doing this, limit of f of x plus g of x, all inside brackets as x approaches, let's just say, for instance, the number 0. Then that means that limit as x approaches 0 of f of x separate plus limit as x approaches 0. Notice it has to be the same. It has to all match up of g of x all there where this plus just gets carried down. That's basically what that means. You can add limits. Next thing is limit as x approaches a of a constant multiplied by the function. Let's think about this one literally for a minute, is equal to the constant multiplied by the limit. So if we have any function, this c will actually stretch the function, where if we have our original function looking like this, and we stretch it by, actually, I'm going to draw a better line for that. That will display this better. If we have a function like this that displays that, and then we stretch it by some exterior y, that means it's going to go up way faster than it goes sideways. So it's going to go like this, then like this. And each of these values are going to be multiplied by whatever this constant stretch is. So that means the limit will also multiply because the limit is dependent on where the graph is at that point. So that just makes sense because that's how stretches work. Now, limit x approaches a to a power is equal to the entire limit to the power. That also makes sense for the same reason that you're manipulating a specific number, which changes the entirety of the graph and how it looks. So that will inevitably also affect the limits. That's just also how that one works. Limit of c as x approaches a is equal to c. So basically, if you're given a graph and c is your function, which means you're given a singular line, either I would say I think it would have to be this way then. Um, as x yeah, it does have to be this way. As x approaches a, so that means as x approaches literally any number is going to always be equal to that. I mean, that just makes sense. It's a straight line, no matter where the limit is, whether it's at -3 or 5 or something like that, it's always going to be equal to that. So it's always going to approach that. And then limit x to the c as x approaches a is equal to a to the c. That makes sense because the limit here, if we have limit x to the c, and then as x approaches a, all you would then do is just sub in this a for an x if you want to solve for a limit, because nothing stops you from subbing in this thing except for if you have a 0 in the denominator, and then it's just equal to a over c. This final one here, limit of x of a, and notice this one is actually a very similar thing to the top one we had, except the top one here just didn't include division. This one includes the division because there's an extra phrase that has to get added on here. So limit of a function divided by a different function is equal to the limits divided by themselves, only under the circumstance where the bottom function's limit is not equal to 0, because then you just can't divide. That just makes sense. So that means this can actually just get categorized up here, assuming that both limits don't equal 0, or at least the bottom one doesn't equal 0. Okay, those are our limit laws. Now let's actually get into solving problems. So we're going to have, I'm not going to write the function first, limit as x approaches the number 3 of x squared plus x minus 12 all over x minus 3. Okay, well, first of all, let's think to ourselves. Our first step can be, can we plug it in? Can we plug this value 3 that we're trying to approach the limit for in? Because if we can plug it in, then any side it's equal to is going to be equal to that, unless you have a split in the graph or something like that. But normally when you have something like this, it isn't a split in the graph. So can we plug it into 3? No, because that would give our denominator 0. So there are two ways we can solve this. We can either use algebra, or we can just use plugging it in with a calculator. Speaking of which, I'm going to grab it. And now the algebra version would just be simplifying both of the fractions and seeing if things cancel to eliminate the 0 denominator problem. But I'm going to first show the easier table method that is something you can totally do on tests as long as they don't specify they want you to solve it without a table or using algebra. So let's just think to ourselves, how do limits work? It's how a function acts as it approaches a number, so as it gets infinitely close to that number. So let's just create an x to f of x table here. Let's say our x, we're trying to approach 3, so we want, and it doesn't specify a direction, so we're going to approach it from both sides. So we'll go 2.9. We'll go then 2.99. We'll then go 2.999. Okay? And then we'll also go 3.1, 3.01, and then extend it a little further, 3.001, because that would be getting infinitely closer to it. So, oh, nice. Because 3.1 or 3.001 is closer than 3.01, which is closer than 3.1, so it would show a progression here. Same deal with this one. 2.999 is closer than 2.99, which is closer than 2.9, which would mean it would show a progression here as well, going from left to right, here left to right. So now let's actually plug these things in. So let's grab a calculator. Now I'm going to show you some little calculator tricks you can use to do this. That would make it very easy to do these problems. So if I want to plug these numbers in, I can just do this. So I'm going to create the function, then I'm going to go answer up plus answer minus 12. So every single time I see a variable, I'm just going to replace it with answer and not use the letter x. And then I'm going to go answer minus 3. So now I'm going to press enter really quick just so it'll save the data. It doesn't matter what pops up there. That's a huge number. So now that is our huge nonsense here. So what I'm going to do now is make the answer that this wants equal to the number I want. So we're going to go 2.9. So 2.9, 2.9. So what I'm going to then do is plug this in. Now, because our previous answer was 2.9, every single time this answer here, it's going to plug in 2.9. So that's how we can set a variable nonsense. So that's equal to 6.9. So 6.9. And now you're going to want to be exact on this, or at least as close to exact as you possibly can, so you can get the best numbers. So 2.99 is the next number that we're going to do. So we're going to press enter. Then we're going to go upwards again, then click enter again. So that's 6.99. Can you guess how 2.999 is going to evolve if this is the thing that's going on here? That's 0.999. 2.999. Go to answer again. Answer 6.999. So obviously, as x approaches 3 from the negative side, it gets closer and closer to 7. So let's just say it approaches 7 there. Now let's see how it works here with this 3.1. So we're going to go 3.1, going to scroll back up to find the answer. 3.1, 7.1. Okay, now 3.01, so 3.01, 7.01. And now 3.001, up again to here, 7.0001. Yeah, I said 3 O's there. Didn't mean to. So then you can see now that there's a progression getting closer and closer to the number 7. So that means that because they progress and closer to number 7, and they're both the same numbers, so this would be from the negative side, this would be from the positive side, that means our limit here is equal to 7. So that would be our answer. But that's using one method. We're going to use two methods for this one. We're going to solve it via algebra just so you can see how to do it, because oftentimes your teachers would prefer to see the algebra than to see that you did a table, because all that shows you is that you have no idea how to solve it via algebra. Because as you get more and more further down the road with solving limits via tables, you'll get more and more complex problems that you can't solve via tables anymore. So it's better to know how to do it via algebra than it is to just plug a table in. But if you're just blanking on how something works, just use a table. So now we're going to solve this via algebra. So I'm actually going to take this whole thing and then just take it out of the limit so I don't have to rewrite it every single time. So now what I'm going to do is just simplify everything down until something cancels. Because we found out that there is indeed a limit. It does not exist, it's not a 0, or it's not an infinity. And even if it was an infinity, we would see that there is still a way to find that out. So we're going to simplify this down. So we're going to go, so x squared plus x minus 12 actually can be factored. So x plus 4, x minus 3. Please review algebra if you don't know how I got that. So now we have x plus 4, x minus 3, and then on the bottom an x minus 3. So our objective with a limit when we're trying to solve by algebra is to simplify everything down to the least that it can be, so that way we can try to cancel stuff. So as you can see, an x minus 3 and an x minus 3 cancel out. So then we're left with just a 1 on the bottom and a 1 up here. So we have x plus 4 is our final thing. And now, because x plus 4, we're trying to find the limit of this as x approaches 3, because technically this is the same thing as that for our limits case. As x approaches 3, there's nothing stopping us from plugging in this 3 anymore, which would then just give us 3 plus 4, which is equal to 7. So that is also how we can get 7. This way I actually prefer, because it doesn't involve a ton of time spent on a calculator, and it also is just way simpler. Okay, now let's do problem 2. 2, this one's starting to get complicated. So x plus 3 all under a radical minus, that's supposed to be a minus 3, all over x, and I'm bad, limit as x approaches 0 of this whole thing is the question that we're going to be solving for. So now, what the heck is this one? Because this looks like a whole bunch of nonsense. Although if you've talked about derivatives before, you actually can recognize this, and it kind of looks like how you would do a derivative. But for our case, we're going to pretend that we don't know what derivatives are. Most of you watching this probably wouldn't anyways. So How would we even approach this problem? Look at it. It looks like nonsense. You're probably thinking to yourself, I want to try to combine these two or something like that. But no, just don't. Just don't. So your safeguard with this one is going to be if you see radicals or you see fractions, you're going to want to eliminate those things using, I forget the name of the thing. I always forget the name of the thing. But basically, we're just going to multiply it by the left side plus the opposite sign that's here, the right side, on both sides, or on both numerator and denominator. I forget the name of the thing. There is an instinctive name for what this is, and I forget the name of it because I always forget it. So what we're going to do is multiply it by this, which then, as time progresses, you'll see will actually eliminate that x at the bottom. And when push comes to shove, just do this. It'll make your life easier. So now let's think about how this stuff is going to work. We're going to multiply it by this, and the reason why we can do this is because this one thing divided by itself is equal to 1. So we're going to multiply it. We're going to just ignore that limit sign there and just multiply it. So x plus 3 times x plus 3, both inside radicals, just means you're adding to 1/2. You're just adding to 1/2 exponents up here. So if you're just adding the two 1/2 exponents, it gets rid of your radical. So we have x plus 3 at the top. And now the entire reason why we did this is because if we then multiply this out, this is just a difference of squares, where if we have x plus y multiplied by x minus y, it's going to always be equal to x squared minus y squared, eliminating any xy variables in the center, which means that rad 3 times x plus rad 3 negative plus x rad 3 times rad 3 positive is going to be equal to 0, because that's what a difference of squares does for you. So now that means we can completely ignore everything else and then just move to the final ones. So negative rad 3 times positive rad 3 is equal to negative 3, because it's just the same exact thing we just did. So that means that's what we have at the top. Now let's see what we have at the bottom. Now I'm going to tell you, don't distribute it. Just don't do it, because we're looking for things in the simplest form. So it's actually going to just create more work for you to simplify it. So that's all you have there. These 3's eliminate, because positive minus 3, is equal to 0. And now we have both an x on the top and an x on the bottom. These eliminate as well. Don't say this is 0. Do not say that's 0. It's 1. So now we have 1 over rad x plus 3 plus rad 3 is equal to, or limit x as approaches 0, is now our new thing. Now, nothing stops us from plugging in 0. Because if we plug in 0 for x here, it's just rad 3 plus rad 3. So we're going to do exactly that. We're going to plug in this 0. 1 over 0 plus rad 3 is just rad 3 plus rad 3 is equal to 1 plus 2 rad 3. Answer. Now, somewhere down the line in school, your teachers told you, rationalize the denominator of a root. In calculus and on the AP test, nobody cares. Leave this as this. All it does is waste time. So this is your answer. It's not rad 3 over 6, as would be the rationalization. Don't even bother. You don't need to. Because nobody on the AP test cares, and nobody anywhere else should care. If they care, they'll specify, in which case, give them a slap in your mind. Okay? So that is the limit for that one. And again, just know that you can test it by plugging in numbers very close to 0 and seeing if they become very close to what you calculated for your limit. Okay, now let's do number 3. We have 6 problems total. 3. Limit as x approaches 1.5, that's a weird number, of 2x squared minus 3x over the absolute value of 2x minus 3. Oh god, that looks complicated, but I promise you it's not very complicated. I draw the absolute values very far down. So, what the heck do we do here? Well, let's just take our normal root and simplify everything down until we can't simplify anything down anymore. So before then, we have to then start using some theory of math to eliminate those absolute values. So 2x, there's both an x here, so we're going to go 2x minus 3 multiplied by x, leaves us with a 2x minus 3 under absolute value. Now we're just going to ignore that limit for now because we can. So let's think for a minute, how can we split up these absolute values? If we're trying to solve an absolute value normally, what we would do is we would set this equal to 0. We would go 2x minus 3. If this was a function where we were trying to solve for 0, we would go 0 is equal to 2x minus 3, and then we'd split it up into its positive and negative parts. We would basically say 0 is equal to negative 2x plus 3, and 0 is equal to positive 2x minus 3. So we would try to split it up. We're going to do the exact same thing with this here, except we're going to make it a little bit more calculus-y. So we want the limit as x approaches 1.5. Notice that x approaches 1.5 is the perfect number to make these not able to be plugged in, which means as you approach from the negative side, you're always going to have what kind of number? If you approach on the negative side, you're going to get always a number less than 3 here, which means minus 3, it'll always give you a negative number. So limit as x approaches 1.5 from the negative side of this function up here, would become x 2x minus 3, and this will always be negative. So we're going to have negative 2x minus 3 as it approaches from the negative side. Now we're going to do the same thing with the positive side. Limit x approaches 1.5 from the positive side. Same dealio, x 2x minus 3. As we approach from the positive side, this number will always be greater than 3, never equal to 3. Same with this one, never equal to 3. This one will always be greater, which means you'll always be left with a positive number. So that means we're going to go 2x minus 3. Okay? Now we're just going to solve it with these limits here in place. These eliminate, we're left with a 1. These eliminate, we're left with a 1. So that means limit as x approaches 1.5 from the positive side is equal to x over 1. Plug in this 1.5 is equal to 1.5. So that's 1.5 from the positive side. So now let's do it for this one. This is negative 1, which means it's equal to negative x, which means if we plug in 1.5, it's equal to negative 1.5. That's on the negative side. So negative side is negative 1.5. Positive side is positive 1.5. We're looking for from either side. These are not equal, which means our total answer does not exist. Such an unsatisfying thing to approach after all that math. All of a sudden just does not exist. Yeah, that's it. So that is how this limit would work. Just note that this wouldn't become suddenly a positive here because, we're trying to absolute value it, which means that everything just becomes positive again. No, not how that works. Just no, because you're approaching from the negative side and you factor in the absolute value by splitting it up. You then eliminate it with that step, not with this step. You don't keep it there because then you would split it again and you would just do nonsense. So that's how that one works. Now let's go to 4. Limit as x approaches 0 of 1 over x minus 1 over x squared plus x. Oh god, that one looks complicated as well. So, first thing we're going to try to do is we're going to try to get everything into one number, one rational function, as opposed to being two rational functions. One thing that our limit laws tells us we can do is split them up. But we're not going to do that because actually, if we were to split it up here, we'd be left with a limit as x approaches 0 of 1 over x, which is just straight up unsolvable until we get to limits as x approaches infinity. But you can also just use some thought to try to get through it, but then you would have infinity plus something else, and we're not going to do that. So what we're going to do is we're going to try to find our least common multiple between these two. So first we're going to simplify them down, because that could automatically give us 1. There's two x's here. X plus 1. Hey, looky low. It actually did give us 1, which means all we have to do, because this side is already to the maximum amount it needs. It's just like, it's kind of like having 2 and 10, where all you have to do is move this side, because 10 or 2 is already a factor of 10. All you have to do, I'm going to use a different color, is multiply this side by x plus 1 over x plus 1, which is equal to 1, which means we can do that. And then that would make our bottom equal to x times x plus 1, which means we would be able to subtract. So I'm going to combine them all in one step. I'm just going to say x times x plus 1. And then we're going to have x plus 1 times 1, which is x plus 1 minus 1, because that side doesn't change. So now all of a sudden we're left with x plus 1 minus 1. These two x's eliminate, or these two 1's eliminate. Then these x's eliminate. That's left with a 1. That's nothing anymore. So now we're left with 1 over x plus 1 is limit as x approaches 0, which nothing stops us from plugging in this 0 anymore. So plug in the 0, it's equal to 1, because 1 over 1 is 1. Okay? Now that is the limit of that. So when in doubt, either rationalize or combine to one function, and then simplify by elimination. Now let's go to number 5. This one and then one more. X approaches 3. This one's actually really easy. X plus 4, 2. Okay. Now, you may be very tempted immediately to try to put out this 2 there, because you're so used to trying to simplify things down or something like that, move things around to try to solve. But notice, is there anything stopping us from plugging in this x, or plugging in this 3 right now? Absolutely nothing. So let's just plug it in. 3 plus 4 squared is 7 squared, 49. That's it. That's literally it. Because you just plug it in. Okay. Now, let's go. Okay, here we go. Number 6. Where did my pen go? It's gone. There it is. Found it. 6. Limit as x approaches 2 of x squared minus 4 over x minus 2 for x is less than 2 of a piecewise function. This number minus this number for x is greater than 2. There we go. So, limit as x approaches 2 for x greater than 2, limit as x is less than 2. First of all, we can't plug either of those in, so we're not going to. We're going to see how it acts as it approaches this from any side, so we're going to split it up. Limit as x approaches to negative, and then limit as x approaches to positive. So first of all, the only thing that we can use to approach from the negative side is this top one. So we're going to use the top one. Okay, and then we're going to do the same thing over here. X approaches 2 from the positive side. What is it here? So we can only use this one as it approaches from the positive side. So x squared minus x minus 2 over x squared minus 4. And now we'll just do the same thing we've done before and simplify it a bunch of times. So limit here, we'll ignore this for now, is x plus 2, x minus 2, x minus 2. These two cancel out. That's 1, that's 1. So you get x plus 2. Plug in this 2. It's not a negative 2, it's just a 2. So 4. So 4 bubble from the negative side. So now we'll simplify this down. We get x minus, we get, so x minus 2, x plus 1 over, no brain farts, x minus 2, x plus 2. These two eliminate 1, 1. So then we're left with x plus 1 over, that's not x plus 1, x plus 1 over x plus 2. Plug in a 2. This is a positive 2, but that's not told by that. So 2 plus 1 is equal to 3 plus 2, 4. So that's what it is from the positive side. These two are not equal. Does not exist. There we go. And that's limits done. Whew! That's the basic gist of limits. Okay, a little bit of a rant here, a little bit of a vent. I just recorded the entire previous part, hence the break between 5 and 6, um, with it in vertical cam, portrait mode, not in landscape mode. I am very angry about that because all that means is I'm going to have to spend an extra 15 or so minutes waiting for it to rotate. Ugh, help. Okay.